by KVA, State and KMCC organization, for her work in the field. She is currently working with Dr. Ebru Erbay on the development of microRNA-based therapeutic approach for the treatment of atherosclerosis. In addition to this formal information, I want to give information about Dr. Kocatürk.
My fiancé wants to give some information.
Dr. Kocatürk is very helpful, thoughtful, and cheerful. Whenever I need help, both research related or personal, she was with me. I really want to thank her. And I believe she will be a good PI and academic advisor in the near future. And the stage is yours.
Thank you for doing my Okay, this is basically a publication that we just published in Science Translation Medicine. So we actually found a novel fat that is not a bad fat, but actually a good fat. So let's start. Do you mind if I sit like this? Is it so informal, or because we are like students, you know? Okay. It's more comfortable. Alright, so first things first. So basically, as a team, we're working on atherosclerosis. And I will describe what exactly atherosclerosis. So atherosclerosis is basically the hardening of your arteries, okay? What happens is that actually in your arteries, there are 3 layers. And it's called intima, media, and adventitia. In the intima layer, endothelial cells are lining in here. On the media layer, smooth muscle cells are lining, but on the other hand, in the adventitia, we got fibroblasts and mast cells. In a disturbed shear stress in the arteries, this endothelial cell starts to express some receptors. And these receptors are against monocytes. They're basically ICAM, BCAM, those kind of things, okay? So as they start to express these receptors, these pink things, monocytes on the blood flow got stuck to these receptors, and via an action called diabetes, they got infiltrated to the media layer, okay? Actually, they are not there, but they are getting infiltrated in a disturbed flow. And as you eat more fatty food there, the macrophages, as they get over there, they start to clear those fatty food by eating them. And they are forming a new structure called foam cells. They are basically macrophages filled with lipids, okay? These foam cells are bad because they release some cytokines, okay? And this inflammatory environment in there is not really a good thing. So what happens is that as they accumulate, the lipid core is formed, okay? And eventually, on the other hand, as they are making some bad things in here, the lipid core is forming, the other parts of the body try to rescue this situation by sending some smooth muscle cells over there, okay? These smooth muscle cells start to go to the fibrous cap. This fibrous cap is actually quite prone to rupture. And the smooth muscle cell acts like a seal over there, okay? It acts like a plug over there. However, as things get really dramatic, as you can see in here, as the lipid core forms, this cap cannot handle the pressure anymore, and it ruptures. So as it ruptures, the content of this lipid core gets exposed to the blood. And one important thing about the macrophages is that they carry the initiator of the coagulation cascade, which is called tissue factor. And as the tissue factor gets in contact with the blood, the coagulation factors that are in the blood are coming in contact with the tissue factor, thus eventually you're forming a thrombus in your artery, okay? As a result, this is what happens. So the thrombus is formed, right? And it gets big in such a way that the blood flow does not take place anymore. So you're having a cease of blood flow, and eventually you might end up with a stroke, and actually the death are actually the main cause of death globally. And in 2012, 31% of these deaths in the world comes from cardiovascular diseases. So we really need a solution for this problem. Okay, what causes exactly to these cardiovascular diseases? Smoking, unhealthy diet, obesity, low physical activity, and alcohol use is actually part of it. In our experimental setup, we actually focused on the unhealthy diet part. So, World Health Organization tried to develop some strategies to make actually the unhealthy diet healthy. How are they planning to do it? They increase the taxation in the food with fat, sugar and salt. That's their proposal for making the diet healthy. But of course, they're trying to make the fat. They're trying to show the fat as the bad guy. But our question arose, and we thought, like, are all the fats really bad? That's our question, okay? So, as you think of fats, this is the first thing that comes to mind, right? Like, this is the guy that pops on your mind first. However, there are three types of fats, and not all of them are bad. We have saturated fatty acids, and we generally take these kind of fat from animal foods. And what's known about the saturated fats is that they actually increase the cholesterol levels in your plasma. The monounsaturated fats, on the other hand, comes from plant foods, and they have a decreasing role in the cholesterol levels in your blood. Moreover, the polyunsaturated fatty acids, they are those famous omega-3 and omega-6 fatty acids, and they even have a more beneficial role in lowering the cholesterol level in your blood. So obviously, by looking at this scheme, we can safely conclude that not all fats are bad. So we thought about it, and we thought, like, okay, we're going to have a bad guy in our experiment, okay, and we need a saturated fatty acid for that. And in our story, we picked the palmitate as our bad guy. And it's actually the most common saturated fatty acids in organism. And what is known is that if you get a lot of carbohydrates, they're converted to palmitic acid. And you can take the palmitate from butter, cheese, milk, meat, cacao butter, soybean oil, and sunflower oil. The other thing that we need to know about the palmitate is that it's also involved in some post-translational modifications of the proteins. And what I mean by that is palmitylation. So it's basically the attachment of a lipid group to a protein, okay? And what it does to this protein is that it changes the protein-lipid interaction, it changes the protein-protein interaction in the membranes, and it changes the tracking of proteins on membranes. So those are three important things that we need to remember. One interesting thing, because we are an atherosclerosis group, and eventually we will work on atherosclerosis. So we wondered what exactly happens to this palmitate in the atherosclerosis patients. And a publication by Chen showed that if the patient suffers from atherosclerosis, the level of palmitate in the plasma increases. So it acts as a marker, okay, for the atherosclerosis. So the other thing is that generally in the literature, the enemy of these bad saturated fatty acids is generally unsaturated fatty acids. For instance, let's have a look at this publication. Olagliptin prevents saturated fatty acid-induced ER stress, inflammation, and insulin resistance in skeletal muscle cells through an AMPK-dependent mechanism. Okay? This saturated fatty acid obviously causes ER stress, inflammation, and insulin resistance. These two guys are also quite important in the development of atherosclerosis. So if we can actually prevent the effects of these saturated fatty acids on these two guys, it's going to be great. And that's our aim in this paper. So, to make things even more clear, the unsaturated fatty acids are Batman, and the saturated fatty acids are Joker. Okay? Those are bad guys. So, as our savior, as our hero, we picked the palmitoleic acid. Okay? And it's a monounsaturated fatty acid, and it's found in all tissues, but mainly it's in the liver. And macadamia and sea buckthorn oil contains high levels of palmitoleic. What is also known is that palmitoleic increases insulin sensitivity, suppresses pro-inflammatory gene expression, and improves hepatic lipid metabolism in diabetic mice. And suppressing pro-inflammatory thing and improving hepatic lipid metabolism are quite useful when it comes to the treatment of atherosclerosis, right? So all these things kind of give us a hint that we can really work with palmitate and palmitolate in an atherosclerosis setting. Other publications also show that palmitic acid actually induces atherosclerosis by impairing macrophage cholesterol efflux and eliciting inflammation. So obviously this palmitic acid has something, it's changing something with the macrophages. And that's why in all our data we use macrophages as our model system. Okay? And in the second part, the fatty acids induce NLRP3 inflammasome activation. Okay? And what exactly is inflammasome activation? Is that this is how the inflammasome activation works basically. To be able to activate an inflammasome, you need two different signals. Okay? The first signal is NF-kappa-B activation. When the NF-kappa-B gets activated, the pro-IL-1 beta it's produced, it's expressed. In a second signal, second hit in here that comes from calcium flux, mitochondrial loss, mitochondrial damage, autophagic dysfunction, and TXM. In the second signal, this NLRP3 inflammasome complex associates with each other and forms the active caspase-1. So the pro-IL-1 beta that is produced by the signal 1 is cut by the active caspase-1 coming from signal 2, and eventually we get mature IL-1 beta. Okay, this is how NLRP3 inflammasome works. And in order to see if NLRP3 inflammasome works, there are two readouts. The first one is the active caspase-1, okay, that comes from signal 2, and the second one is the mature IL-1 beta. Okay? So, as I mentioned before, we are working on macrophages. These are the guys that makes all that cytokines and stuff in the atherosclerotic plaque. So, now we're checking the if NLRP3 inflammasome gets activated or not. The first readout, IL-1 beta, right? We checked it in the supernatant of macrophages. And as we treat the cells with LPS, that makes the signal 1, and palmitate makes the signal 2. As you can see, the IL-1 beta levels are quite high. However, if we give also palmitate to that, the level diminishes drastically. The second readout is caspase-1, right? And as you can see in here, as we give LPS plus palmitate, you see there's a big caspase-1 there. And when we give the palmitate on top of palmitate plus LPS, it's gone. So obviously, palmitate prevents inflammasome activation. Okay, then we wondered, because palmitate induces, we know that palmitate induces NLRP3 inflammasome activation, but there are other chemicals that also, causes the NLRP3 inflammasome activation. And those are these three ones, chitosan, ATP, and alanine. What we did is basically, okay, so one by one, we first gave LPS plus palmitate. There is a big, caspase there. However, if we give like palmitate to that cell, it's gone. So it's really diminishing the NLRP3 inflammasome activation. However, if we treat the cells with chitosan or ATP or aluminum, as you can see in here, the level doesn't change, doesn't matter if I give palmitolate or not. That's the first thing that we need to keep in mind. Palmitolate only affects the palmitate-induced NLRP3 inflammasome activation, okay? That's number one. Number two, there are other inflammasomes in our body. And those are AIM2, NLRC4, NLRP3, NLRP1. We also use chemical inducers for that. And what we found out is that, as you can see in here, as we induce the AIM2 activation, palmitolate, even though I give palmitolate, there is no change. NLRC4, the same story. NLRP3, the one story. So, what we can conclude from this two Western blots is that PAO only blocks lipid-induced NLRP3 activation. Okay? Okay, we have the inflammasome activation going on, but this is not the only pro-inflammatory cytokine that's residing in the atherosclerotic plaque. There are many others, and we also wanted to have a look at them. And what we found out is that as we give palmitate plus LPS, the TNF levels are increased, but with PAO, it's decreased. Same story for IL-6. As we give palmitate, it's increased. With palmitolate, it's decreased. Same story, okay? So obviously, PAO blocks pro-inflammatory cytokine expression. Okay, the other thing that I want to talk about in here, when I was showing you the NLRP3 inflammasome activation, I told you that the signal 2 also comes from mitochondrial growth. And we also wanted to check if actually palmitate and palmitolate has an impact on the mitochondrial growth production. Those are reactive oxygen species. They're not really good for your body. So what we found out is that when we treat the bone marrow derived macrophages with palmitate, the level of, as you can see in here, the level of the mitochondrial growth increases, okay? However, when we give LPS palmitate and palmitolate, it's again diminished. So it also, kind of blocks this side, the palmitolate. Okay, so these are lipids, and there are different lipid classes, right, in the body. There are good guys, for instance, HDL is the good guy, LDL is the bad guy, blah, blah, and also there are neutral lipid classes in the body. When the fat goes there, it's not really harmful anymore. Like, it acts like a jail. So I'm trying to make a story in here. So think palmitate as a gang member, okay? And palmitolate is basically the policeman. And policeman catches the gang member and puts it into this neutral lipid stores. I call it the jail, okay? So it cannot really do bad things anymore. This is what we also found. It's 3-acylglycerol neutral lipid store. And the palmitolate actually, when you have a look at this spot, when we compare palmitate plus palmitolate with palmitate, its levels are increased. So this is also something that we found. But as a team, we are famous with our endoplasmic reticulum stress studies. And we also know that atherosclerosis is really badly influenced by endoplasmic reticulum stress. And my supervisor, Dr. Ebru Erbay, actually found that when you reduce endoplasmic reticulum stress, you can have a beneficial role on the atherosclerosis. So, what is endoplasmic reticulum stress? I'm going to give you a brief introduction about that. Those amyloidogenic neurodegenerative disorders, right? Like the mutant proteins, like prion disease, the mutant proteins have a tendency to get stuck and accumulate. This is just an example. These accumulated proteins in the cell, okay, the body is kind of like this. I'm having so much misfolded protein in me, and I need to get rid of them. That's why it starts a machinery called endoplasmic reticulum stress. And it has three arms. the PERK, the IRE, and ATF6. I'm not going to really go into about ATF6 are, but we know that saturated fatty acids activate both of these parts, and basically these guys are residing on the endoplasmic reticulum, because endoplasmic reticulum is actually the place in the cell that folds all these proteins. So if something goes wrong with the folding and there are misfolded proteins are going on in the cell, it should be the endoplasmic reticulum who needs to do something about it. So we have the PERK arm and IRE arm. Let's have a look at that. When the PERK arm gets activated, it makes a homodimer in here, and it phosphorylates the substrate EF2 alpha. As the EF2 alpha gets phosphorylated, it causes a translational attenuation in the cell. Why does it happen? Because the cell already has a lot of misfolded proteins in it. It doesn't need any more proteins coming, right? So it says like, okay, I have enough already, I don't want anything new coming. So it should first stop the translation. The second arm, on the other hand, is IRE. And this IRE, when it gets activated, it makes a homodimer and it's phosphorylated. Then it cuts the XPP1 mRNA, thus it causes an active transcription factor. This transcription factor then goes to the nucleus and causes the expression of chaperones. And what are chaperones? Those are proteins that helps to fold the protein. And it obviously needs some of those because the proteins are misfolded, right? So let's focus on the inner surface part in our study. As I mentioned before, the IRE basically works as a homodimer. So it should oligomerize itself first to get activated. So we have this special plasmid courtesy of Peter Boulder, UCSF. What it does is basically as the IRE gets oligomerized, it's ends up as a dot. It's GFP labeled, but it's not a smear anymore. It ends up as a dot, okay? And as you can see in here, palmitate, when we give palmitate, there are lots of dots. So IRE gets oligomerized and activated, obviously. On the other hand, when we give palmitate plus palmitolate, the dots are not that dramatic anymore, okay? And this is a quantification of that. The other thing is showing the IRE bond activation is its phosphorylation state. And again, when we give palmitate, the IRE gets phosphorylated, but when we give palmitate plus palmitolate, it's not really there anymore. The same story holds for spliced SPP because IRE gets activated and it, spliced the SPP. Palmitate splice the SPP, but palmitolate diminishes that effect. So obviously, from this scenario, it's clear that palmitolate downregulates palmitate-induced ER stress. The next thing that we want to know, because IRE obviously gets oligomerized, right? And how does it happen? Because in order to get oligomerized, two IRE molecules are on the membrane, ER membrane, but they should get close to each other, so they should be able to move in the membrane, right? And we are known from the literature that palmitate actually increases stiffness of the membranes. So if the membrane gets stiff, right, how come two things get close to each other, right? You need some kind of a relaxation in the membrane. That's why they can come close to each other. So we wondered that does palmitolate get incorporated into the membrane of the ER, because it might, remove that stiffness and so on. And actually it does. So we isolated ER4 macrophages, and as you can see in here, the palmitolate gets really incorporated there. The other thing that we found out is that when we isolated ER4 macrophages, it is actually mainly end up in cholesterol ester and phospholipids, and those are the parts that reside on the membrane of the ER. Okay, so then from this data, it's clear that palmitolate incorporates into the ER membrane. atherosclerosis comes next. And because we are thinking palmitoylate as a diet, yeah, I mean it's good as a diet. So we made oral lavage to mice for 4 consecutive weeks. And the part that gets the most damage in the atherosclerotic mice is this aorta. And as you can see here, all these white things are fat that's accumulated in the aorta. So in order to see an effect, in order to see a beneficial effect on atherosclerosis, one should be able to target its substance or its drug to the aorta. So that's what we did. We want this palmitoylate to end up in aorta. And when we isolated aorta, we saw that the palmitoylate concentration increases with the mice as we oral lavage them. So that was a good thing overall, because, I mean, then it works for an atherosclerosis study. The next thing, we check the lipid levels in the aorta. These red guys are the lipids, okay? And the lesion area, as you can see, as you take palmitoylate, it decreases. This is the part that aorta makes an entry to heart, and the lesion area also decreased in that part. As I mentioned in my first slide, the atherosclerotic plaque contains many different cell types. Okay, so then we wondered, okay, we are having a decrease in aorta, but what happens to the other cells? What happens to their levels? We found that the macrophages, these were the red guys, these are the foam cells, they decrease. So that was a good thing. The other thing is that the other good thing is that apoptotic cells decreases. What is the good thing? Because as the cells get into the apoptosis, okay, they form a kind of core, and it's called necrotic core in the atherosclerotic plaque. And as the necrotic core gets bigger, the plaque becomes more vulnerable and it becomes more prone to rupture. So it was a good thing that we saw less dead cells. Okay? T cells, there were no change. So as I mentioned in my first slide again, the smooth muscle cells has a tendency to go to the fibrous cap and seal there. So they are good guys, but we couldn't, although there's a trend, we couldn't reach their significance with that. And collagen again helps smooth muscle cells to seal the fibrous cap. So this is also a good guy, and it doesn't change with palmitoylate administration. So overall, it shows that the palmitoylate actually reduces the bad guys, but does not really have an influence on the good guys. Okay. So of course, the next step was to check the endoplasmic reticulum stress in the lesions. We used two different markers for that, EF2 alpha and ATF3. And if we have a look at the fluorescence intensity in macrophages, these are lesional macrophages. So if you have a look at it, the endoplasmic reticulum stress obviously decreased in the lesional macrophages. Okay, so that was also a good thing. The last thing is to check the inflammasome there, right? Because in an in vitro setting, we saw that palmitoylate actually diminishes the NLRP3 activation. So we had a look at the IL-1 beta levels, and we found that actually in the lesion, its levels here decreased. We also want, because it's a chronic administration, like, you just eat it and it will go everywhere. We also want to check IL-1 beta levels in the plasma. We check on the plasma level. And again, in a chronic way, IL-1 beta level basically decreases. Okay, now in a nutshell, this is my conclusion slide. The palmitoylate in here goes to the ER membrane, okay? And this IRE1, it goes to the ER membrane and it remodels it. And lipid-induced ER stress and activation of UPR is blocked by that. Mitochondrial growth levels are also diminished with palmitoylate. This prevents the activation of NLRP3 inflammasome. Consequently, IL-1 IL-6 decreases, and then in overall it acts as a shield for the atherosclerotic plaque progression. Of course, this study took so many people's help, and most of them are here. I want to thank them. And we also have some honorable collaborators in here, like Bilkent and Begüm. And I want to thank my supervisor Ebru for helping us with the study. And I want to thank you all for your attention.
If you have questions, we will give some questions. Do you have questions?
Which nutrients were rich in folate ingredient? I mean,
It's pure. Pure palm
which
ingredient? What should I eat?
what should I eat? Yeah.
Macadamia oil and sea buckthorn oil. İğrenmiyor.
Is there any question? If not, I will ask a question. What about instrument-related stability during your activity?
We did it every day. We did it every day.
Every day.
Every day.
Okay. And I will ask, what if we give this formula as a, how can I say, local or systemic delivery? Which one will be beneficial?
Yeah. You know what's the deal about this? I mean, when you're making a paper, I see those kind of things, like they're giving by injection, but you know, we're trying to change nutrition way. So we could have administered it like that, very dramatically, like just push it to the bloodstream and then it will go everywhere, you know, all this. But that doesn't reflect, because when a person has, we're trying to change their nutrition style, okay? And the way to go there is by glucose, because you need to make that thing, you know, eat it. That's the reason why we do that.
Actually, I'm asking for if we produce a material and encapsulate it formally and coat this material with and how can I say, deliver that to that atherosclerotic plaque or dimensional thrombosis or etc. Will it work? Same, I guess.
I don't think palmitoid has an impact on, has an anti-thrombotic effect, but it might, of course, as the plaque gets smaller, it won't have a tendency to rupture. But yeah.
Because in atherosclerosis, for bypass patients or angio patients, when they deliver a stent to artery, atherosclerotic plaques come and close stent, and it causes restenosis of stent. So I'm asking that can we functionalize stent with formula to prevent several stent applications?
So this is the discussion that we had with Dr. Irvine asked. Because the first question that popped up in my mind in this study, are we trying to prevent the atherosclerosis formation, or are we trying to heal people? You know, there are two differences, because you might not get it at all, you know, with a healthy lifestyle, or you might just have it, atherosclerosis plaque form, and then, you know, you just use it as a drug, and then try to, you know, diminish it. But I think in our scenario, it's the first thing, like, you get it, that's why you want to, you know, have a healthy lifestyle. So that's something.
If you don't have questions,
Sen yol arkadaşım, sen nasıl bana soruyorsun arasında?
Tabii ki yol arkadaşım olduğu için soruyorum. What do you think, how the specificity to NLRP3 inflammasome is achieved by palmitolate? So why it's only specific to NLRP3?
Maybe macrophages has something to do with, you know, NLRP3 inflammasome activation, and NLRP4, and the other ones are not that, because see, when we have a look at the Although I know you're going to make a comment now, but let's have a look. So, you know the dancing here, like they're really thick. See, in the macrophages. However, on the other hand, I know you're going to say about M2, but these two guys are not that much in the macrophages, you know. So maybe they're not the dominant inflammasome in those cells. The level is too little, at least with the NLRC4 and NLRP1, that, you know, doesn't really matter. Do you have any idea? That's what I can talk about.
Do you have more questions? If not, we want to thank Dr. Kocatürk for being our second speaker in our graduate seminar series. Thank you very much.
No problem.
Ben de dışarıdaydım ya, işim vardı.